5.4 concavity and second derivative test. Now, in the title of this, you probably know exactly what derivative is and how to find a second derivative, hopefully. But concavity might be a totally new thing for you. So probably the easiest way to talk about it is by looking at these basic parabolas, right? So we have one facing up and facing down, okay? Now, if we look at the one on the left, look at my laser pointer. The one on the left here, see how it makes that little curve up like that on both sides? This will be concave up, okay? Everywhere it's concave up with just your y equal x squared, okay? It gives the graph this little curve shape like this when it's over here, and then curve shape like this when it's up here. Certain graphs are going to have this shape whenever we don't have a straightforward like x squared graph or negative x squared graph. We're going to have to be able to tell when is it going to have this nice little curve up, or if it's decreasing, still have that little curve up shape to the graph. And then down over here, your negative x squared graph, see how it has this little curve like that? That would be a concave down when it does one of these, okay? When it has a little shape like this on your graph, it's a concave down, okay? Key thing here, keep in mind, look, you're decreasing over here, right? But you're concave up. Just because you're concave up or concave down does not necessarily mean your graph is increasing or decreasing. It could be vice versa, it could be flipped. Like, it could be the value of x is increasing right here, and the value of y is increasing, but you're still concave down right here, okay? So that's something to keep in mind whenever we are trying to tell if it's concave up or concave down. It's solely based about what you'll see is in the next slide is, or not next slide, I guess in 2 slides, you have to test for it using your second derivative. Alright, a formal definition of concavity. If f is differentiable on an open interval, the graph of f is concave upward. Give me this. I don't want to move that. Concave upward on I if the derivative of f is increasing on the interval, and concave downward on I if the derivative of f of x is decreasing on the interval. So this is like a repeat of increasing and decreasing function and telling that, right? Because we were able to tell if the original function f of x was increasing based off the derivative, and if it was decreasing based off of the derivative. Same story here. If the derivative of f of x is increasing, it's concave upward. If derivative of f is decreasing, it's concave downward. So it's a similar process as before. You're just finding the derivative one more time, and it's going to tell us what the concavity is as opposed to whether it's increasing or decreasing. Alright, testing for concavity. So we have the function f of x, and there's a second derivative that exists on the open interval. If that second derivative is greater than 0, it's concave up. If it's less than 0, it's concave down. I would recommend pausing this so you can write this down, but that's essentially all it's saying. You find the second derivative, values that are greater than 0, it's concave up. Less than 0, makes it concave down. Alright, let's use this function right here to tell when a function is concave up or concave down. So we need to find the second derivative. We could use quotient rule, but since there's a number up top, let's make our lives a little easier and do this. A little sneaky here. That's 12. And make this a negative first. That way we can just use our chain rule. Fun. Negative 24 times quantity x squared plus 12 to the power of negative 2 times the derivative of the inside, which is 2x. That was much easier than the quotient rule, huh? And then let's make things look a little nicer. Let's do a negative 48x over, now we have to use quotient rule, darn. That's the derivative. Now we have to find a second derivative. That's going to be x squared plus 12 squared times negative 48 x squared plus 12 to the fourth power, because that's going to square that bottom, and then you're going to get negative 48x times 4x, because of chain rule, parenthesis, x squared plus 12. Let's do some simplifying, and it's going to be a little bit ugly. I apologize. But if we factor out and x squared plus 12 out of both terms, that's going to make things a little bit nicer. And then what's left over? We have negative 48. So it'll be negative 48 x squared plus, or minus rather. What's 48 times 12? That would be 576. And then what's left over here? Negative 48 times 4x would be 192x squared. And then simplify that. We'll get 144 x squared minus 576 there we go. Keep bringing everything else down. I could cancel this out and make that a 3, and really, so there's no values that are going to make the denominator 0, but the numerator, on the other hand, if I set that to 0, I'll make it a different color so we can stand out a little bit. Would you look at that? By just going to your calculator, see the common factors, those are ugly numbers. 144 does factor out, so it'll be x squared minus 4 equals 0, so x equals 2 and negative 2. So all that works is to find negative 2 and negative 2. That's funny. So what can we do? What we can do is just like what we did, increase and decrease, we need to test the interval, okay? So on next page, I'm going to make a chart, and we are going to test them. Alright, so I wrote the function over again, and we're making our chart. Keep in mind, I don't really care what the exact number is. I just care if it's positive or negative. You don't need to find, because we have some big numbers here. So clearly you're going to get some goofy answers if you actually find out what exactly it is. I care, and you should care, about whether it's positive or negative. That's bottom line. Okay, so we have to test 3 different numbers out. F double prime negative 3. What happens when we put negative 3 in? Denominator, negative 3 squared is 9 plus 12 is going to be, that's going to be positive. Negative 3 squared is going to be 9 minus 4, positive times positive. We got a positive over a positive, folks, so it's going to be greater than 0. What does that mean? We're concaving upward. Concave upward. 0. That'll get us positive on the denominator, and we're going to get a negative times a positive up top, because it's going to be negative 4 times a positive number, so it'll be negative divided by a positive, so that's going to be a negative. So f double prime is 0, less than 0, so therefore we're going to have a concave downward. And 3, f double prime of 3. Put 3 in, it's going to be positive times over positive, so it'd be positive. That means concave upward. Right? So now we're going to tell exactly with our charts, and by finding a second derivative when it's concave up and concave downward. Alright, Let's determine the concavity of this one right here. So we got f of x equals negative x to the third plus 6x squared minus 9x minus 1. So we need to find a second derivative. If this is something that seems a little off, as far as like, this is a little more difficult, which it is, because this is something that you're going to need to see more problems on. There's some good examples in your book as well, okay? So go in the beginning of that section. I try to pick a variety of questions so that you can see more. Yeah, and plus these sometimes take a while, so I don't want to. I can give you examples and have a 30-minute video, but we don't want that. So let's find a second derivative. And what value makes it 0? That would be 2, x equal to 2. That's an easier one, right? So let's make our chart. Two, and then 2 to infinity. And then what are we going to do? Let's test 0 and test 3. F over prime is 0. That will get us a positive number, so it's greater than 0. So therefore, we'll be concave up. From negative infinity to 2. And then when we do f over prime of 3, that will be in negative 6, so that would be less than 0. So therefore, we're concave downward. Alright, a point of inflection. Point of inflection is basically whenever it changes from concave up to concave down, or vice versa. When we find these points of inflection, by whenever you find a second derivative, it's the values that are set that make the second derivative 0 or do not exist. Okay, so pretty much what we kind of did in the first two problems, right? We found the values that made it numerator denominator 0. We haven't seen one with the denominator yet. If you go to examples in the beginning of the section, you will see an example where there are values that make the denominator 0. But anyway, values make the denominator 0 and the numerator 0. Those are your points of inflection, where we could potentially see a change from concave up to concave down, or vice versa. Alright, let's find the points of inflection here. So we need to find a second derivative, that means. So let's do that. X to the third minus 4x, and then we get 3x squared minus 4. And then we factor. In this case, we're not going to factor. Since it's difference of squares, I can just add 4 to the other side and divide by 3. And square root, and plus or minus root 4 over 3. So those are your points of inflection. X is a little more than 1 and a little less than negative 1 are our solutions. So whenever we set these up, be rather negative infinity to negative root 4 over 3. We're running low in space here, unfortunately. Negative root 4 over 3 to root 4 over 3. And then if I add another column, root 4 over 3 to infinity. So let's pick a value. So x equal to negative 2, x equal to 0, and x equal to 2. Those seem like good values. So we put negative 2 in to this function right here. That will get us a positive value because it'll be 12 minus 4 is 8. So we can say that f over prime of negative 2 is concave up. Going to be concave upward. 0, on the other hand, we test 0, be less than 0, so it'll be downward. And then 2 will get us the same answer as when we did -2. After prime of 2, be greater than 0, so it'll be concave upward. Alright, the second derivative test. Let f be a function such that the derivative of f of c is equal to 0. So basically what this rule is saying is that you can use the second derivative to tell whether it's a max or a min. Okay? If at that value that makes the first derivative 0, you find a second derivative and it's greater than 0, it would be a minimum value. And it'd be a max if it was less than 0. Okay? So the values that make the first derivative 0, plug whatever that x value is into your second derivative, it's greater than 0, min, less than 0, a max. Alright, let's give this second derivative test a go. So we find the first. And then we got this for our first derivative. Now we need to find the zeros. One of them is going to be x equal to 0, because I'm just going to straight up factor a -4x out. Leave me with x squared minus 3x minus 4. Factor that more. And we're going to also get x equal to -1 and x equal to 4. Now, we need to tell if they're a min or a max, so we have to find the second derivative. We're using what we had up here for the first, okay? When we do that, -12x squared plus 24x plus 16. GCF is 4, to make our lives a little bit easier. And we still have to use AC, so factors of -12, the add is 6. Wait, never mind. We don't need that. We just need to see if these values make it negative positive. So when we put 0 in, it becomes positive, right? So what does it mean when it's positive? That means x equals 0 is a relative min. -1. -1 will get us -12 plus -24. That's going to be a negative number. So when it's a negative number, it will be a relative max. 4. 4 will get us -80. -80 is less than 0, so therefore it's a relative max. Right? And that's it. I appreciate you watching, and we'll see you later. Bye-bye now.